Okay, hopefully my voice will hold out for this. But Monday we have test 4. There are 20 problems. So each one will be worth 5 points. You could probably pretty much guess what those problems will be like. Several will be find the indefinite integral, or we also call that the antiderivative. So we looked at a lot of different techniques for that, just kind of the reverse of your derivative rules. We have the antiderivative power rule, all the trig functions. You got to kind of think what's the derivative of a trig function, and then the antiderivative would be what it starts out with. The exponential and the log. 1 over x dx, antiderivative would be natural log of x. And in all these antiderivatives or indefinite integrals, do not forget the plus c. That is part of the answer.
That's only for indefinite.
Correct. That is only for the indefinite integrals or the antiderivatives. When we get to the definite integrals, we don't need the plus c, because the fundamental theorem of calculus, it's f of b minus f of a. So even if you put the plus c in there, when you do the subtraction, the constants would cancel out. So we don't need it for the definite integral, but definitely need it for the indefinite integral. Okay. Now, these are kind of the basic antiderivative rules, but also we spent quite a bit of time on the substitution. And the tricky part there really is, what shall we let u equal? Sometimes it's fairly obvious, but there's other times where we have a choice of about 3 or 4 different things. Now, another thing we've got to watch with this, sometimes it may look like we need substitution, but there are times where we can simplify algebraically, and then each part will integrate fairly easily. And we see that a lot with fractions. Okay. If we have something like this, what would we need to do if we were to integrate this?
Put it all over mix.
Simplify, which we'd have x squared. Of course, I run out of room here. We'd have x squared minus x plus 2 over x. And now they turn into basic antiderivatives. And we'd get x cubed over 3 minus x squared over 2 plus, 2 times the natural log of x plus c. Now, one quick mention on this natural log of x, we do need the inside to be absolute values. We'll see that a little more when we use this in the definite integrals. If there's any negative values on our integral limits, we would need the absolute value in there. We cannot take the natural log of a negative, but we can end up with an antiderivative with a natural log. But we need the absolute values on the x. Okay? So,
Have you simplified by diagonal? I thought it was like the entire, okay, I see.
yep. If there's just one single term in the denominator, that's a good indication we've got to separate it into fractions, simplify your fractions, then you're ready to do the antiderivative. And if I remember right, that type of problem was probably the most asked by all of you. How do you do this? Or some of you were looking as during some substitutions and you'd say, well, what can I let u equal? Well, we don't need to let u equal anything, but it is kind of hard to recognize. So make sure, if you possibly can, simplify it algebraically first, then see what you can do for the antiderivative. Now, we did a lot with the indefinite integrals, and then we kind of jumped into what I kind of think is the second part of this particular unit, working with summations, kind of the introduction of that notation, and then the approximating the area under a curve, which eventually led up to the definition of the definite integral. So for the test, there's not going to be anything about the summation. I'm not going to give you a summation of something and have you write out terms or anything like that. But definitely we could have something about approximating area. On the worksheets, I had you do both 4 rectangles and 8 rectangles. Well, on the test, I do want you to get done on Monday, so we'll limit that to 4 or less. I'm not getting, we'll say no n equal 8, but more like n equal 4, maybe n equal 3, something like that. So you can show me that you understand the idea without having to do lots and lots of calculations. But could be the left, using the left endpoints, or the right endpoints, or both. And then again, this led up to partitioning the interval into n subintervals and then using that for the definition of the definite integral. Yes, you will probably have a problem of the definition. Use the definition of the definite integral.
Will it clearly say use the definition?
Yes.
And if we don't?
If it's just evaluate, then you can use the shortcut, the fundamental theorem. But there will be one where specifically it says use the definition. And the definition that's that limit as the mesh approaches 0 of the Riemann sum f of c sub I times delta x sub I. Now, in our setup, we're going to kind of make this a little more specific. In technical terms, the delta x, the width of each subinterval, do not have to be equal, but we're going to make them equal, so that will change this. We can say allow delta x sub I to be equal for all I. We'll get some technical terminology here. So we can say delta x or delta x sub I. To calculate that, we use the b minus a over n, and maybe it goes from 0 to 4. Well, delta x then would be 4 minus 0 over n, or 4 over n. Okay. And by doing that, that changes a couple things just slightly. This then would change to n approaching infinity, and then this would change to just delta x. And then one other thing that we do, technically the general definition uses c sub I, which can be any sampling point we want. Well, we're going to specify, let c sub I be the right endpoint of each subinterval. So like we said up here, we could use left, we could use right, or technically we could use anything in between. It will make it a lot easier just to use the right endpoints.
And that's just because we'd be adding delta x instead of
Correct,
subtracting delta.
correct. Ultimately, x sub I, the x sub 3 would be a plus 3 delta x. So x sub I will be a plus I delta x. Use a different sampling point, and there's a little bit more to it than that. So what you may start out with then is this notation rather than this notation. But a lot of details getting to this. And then once we figure out what the x sub i's are, how to put that into the function, of course, figuring out delta x will be a big part of that. We will have an expression in terms of I, and then we'll be applying that summation. And the summation formulas, you will need to know these, but I will limit those to the summation of a constant, which equals what?
C n, a constant.
Okay, that constant times n, and then the summation of just I. And what is that one?
That one n, and then parentheses n plus 1 over 2.
Okay.
I watched the video.
Those videos kind of help, don't they? But this, I will have limited the results of our summation down to just those two possibilities. On the worksheet, we also had I squared and I cubed. Actually, we didn't have I cubed at all, but these will be the only two that you'll need to remember for the test. Okay. Okay, so lots and lots of steps on that type of problem. And like I said, I'll limit that to just one rather than 3 or 4. But any other definite integrals that you have to find or evaluate, you can use the fundamental theorem. Okay. Questions on the definition? Next up, we looked at the fundamental theorem, and this is the biggie. This ties the derivative and the definite integral together and makes it one branch of calculus rather than two separate branches of calculus. And we looked at two different forms of this. The first one, we start out with the function defined in what looks like a definite integral. And this being defined over some interval. This happens to be number 1 off the worksheet. Basically, from this information, we can calculate the derivative very quickly and easily, or hopefully we can. What would the derivative be for this? Well, it turns out to be simply the e to the x cosine of x. Okay. Essentially, the inside doesn't change because the derivative is the inverse operation of the definite integral, or the integration. So the derivative and the integration kind of cancel each other out, and we're left with this. Now notice the answer is in terms of x, because we're saying what is the function, the derivative in terms of x. Not what is f primed of t, but what is f primed of x. So that's kind of the strange, what I kind of feel like this is the strange fundamental theorem. It looks too good to be true, but it really is just, we cancel one operation out with the other, and we're left with what we started with. Okay. Now, the other side to this is starting with the definite integral. How would we find that, or how would we evaluate that?
Take the integral of x squared.
Okay, the
Outside.
indefinite integral, or the antiderivative of x squared. And some fancy notation here. Sometimes we'll put a line, or if there's 2 or more terms, you'd put brackets. We evaluate this from 0 to 3. And we'd end up with value of 9. Technically, what we end up with capital F is the antiderivative, just like x cubed over 3 would be the antiderivative of x squared. So we take f of b minus f of a. So we always start with the top one and then subtract the bottom one. Okay? And we use that in a lot of different ways. We talked about simply evaluating definite integrals. We also use this in finding area of regions under a curve and above the x-axis. For instance, in this case, we could say this value of 9 is also the area under y equals x squared over the x-axis from 0 to 3. So definite integral can be used in that manner as well. We looked at several different area problems. And then another area problem is, instead of being given a function in equation form, we were given it as a graph. Okay. Now, if this is our function y equals f of x, we'll just make this fairly straightforward here. Integrating from 0 to 6 for this function, how would we calculate that? calculate the definite integral based on the function being defined as this graph.
Or you could use those, you could either like count those little squares out,
Okay.
like geometry wise, or you could use those endpoints and plug them into this one.
Okay,
There is
we-
from 0 to 6.
Yeah, from 0 to 6.
There's a little triangle over there.
So there's a little triangle here. There's a little triangle here. Those two are both above the x-axis, which means what?
It's positive.
Okay, the value of the definite integral will be positive, represented by those areas. And what is that area? Okay. Each area of the triangle would be 1/2, so you get a total of 1 for those. Now, what about the area under the x-axis?
It's gonna be 3, and you're doing the same.
Okay. This rectangle here, area would be 2, and we have a 1/2 there and a 1/2 there. So, but because it's under, the value of the definite integral turns out to be negative. So overall, based on this function, the definite integral value ends up being -2. We got 1/2 minus a 1/2, 1/2 minus a 1/2, and we got the -2 left. So the area represents the value of the definite integral, but you got to watch anything below the x-axis, the definite integral value is negative. Okay?
Does it go down one there in the graph?
Yeah, this is -1 and +1. My graph is not nearly as nice as it should be, but hopefully you get the gist of it. Questions? So these are the ways that we calculate the definite integral, calculate it exactly, and in the last section, we talked about a couple different ways to approximate the definite integral. Some functions we can't figure out a indefinite integral or an antiderivative for it, but we can at least estimate the value of it using, well, we talked about the rectangles earlier, the right endpoints or the left endpoints, but those are not very accurate. The trapezoidal rule, this is much more accurate than the rectangles, and for it, we use the idea of the area of a trapezoid, 1/2 times the height times the sum of the bases. Usually you see it parentheses b sub 1 plus b sub 2. But we're going to split this up, and again, we can use n equal 3, n equal 4. I won't have you do a whole bunch like n equal 50, but you could. You'd get really accurate if you're using that, but probably n equal 4 will be sufficient. The trapezoidal rule is 1/2 times the b minus a over n times, and then here's your y values, kind of like the length of the rectangles that we talked about. This would be the bases of the trapezoid. Now the inside ones will be used more than once. They're going to be used twice, but the first one and the last one are only used once. Now, this is n minus 1, and this is x sub n. So x sub 0 is used once, x sub 1 calculate the function value, and then we multiply that by 2. So again, everything on the inside we'll use twice. First and last we only use once. Okay. And we got this from the Think Well material. Then yesterday I introduced what they call Simpson's rule. And it is actually based on the area under a parabola. Now, like I said yesterday, we probably have never seen the area under a parabola formula before, but it's used in this estimation. Now, in this case, it's not 1/2, but it's 1/3 b minus a over n, and then times. Now the pattern here, again, it's only just one of the first function value, f of x sub 0, but then because of the area formula under a parabola, we'll have 4 times f of x sub 1, and then 2 times f of x sub 2, 4 times f of x sub 3, and so on, 2 on the next one. Then the second to the last one will have the coefficient of 4 times that function value, and then again back to just 1 on the very last one. Same thing with f of x sub n on the trapezoidal rule. F of x sub n on Simpson's rule, we only use 1 times that last one. So again, if you have a lot of calculations to do, you'll see several of these patterns repeated. Well, like I said, we'll probably just limit it to n equal 4 or somewhere around there. So you're not going to see a whole bunch of terms in here for the Simpson's rule. But those you will need to learn, or at least kind of get an idea. Trapezoidal rule uses 1/2, where the Simpson's rule uses 1/3. And then your b minus a over n, well, that's just like delta x. Same basic idea we used with the rectangles. This is the key part in remembering trapezoidal rule and Simpson's rule. So, well, out of all of those topics, I think I can find 20 problems pretty easily. So there won't be a lot of any one thing, but a little bit of everything. Probably a handful of indefinite integrals, a handful of definite integrals, a handful of find the area under a curve, and then probably only 1 or 2 of the more specific type of problems that we've talked about. So any questions, any problems that we want to look at?